Good afternoon, everyone. Thank you for coming to our ship design presentation. We are U.S. Coastal Shipworks, and today we are presenting a concept design proposal for a U.S. Coast Guard special purpose craft heavy weather motor lifeboat. Today we'll go over our industry mentors, we'll introduce our team members, we'll discuss objectives, rules and regulations, major items and systems, principal characteristics, vessel mission systems, the general arrangement, the hull form, the structural arrangement, weights and centers, loading conditions, vessel stability, installed machinery, and then we'll take questions at the end. We'd like to begin by thanking our industry mentors. We have Chris Berry, a private consultant, Chris Carp from the U.S. Coast Guard, Avery Fanning from the U.S. Coast Guard, Ben Fisher from Elliott Bay Design Group, Debu Ghosh from the U.S. Coast Guard, Andrew Muller, also from the U.S. Coast Guard, Darren Monzingo from Faro Industrial, Ian Mutnick from Birdon, and David Shepard from the U.S. Coast Guard. Our team consists of Caleb Brockett from Adamstown, Maryland, Aidan Kavanaugh from Smyrna, Georgia, myself, Andre Klima from Ellicott City, Maryland, Allison Toohey from Lutherville, Maryland, and Harrison Weinberg from Great Neck, New York. Next, we will discuss a summary of our design objectives. These include 34-person capacity, 72-hour endurance and crew accommodations, both enclosed and open bridges, self-righting in 30 seconds or less, 0 fossil fuel emission for at least 24 hours, and an overall 25% reduction in total fossil fuel use compared to similar vessels, Bureau Veritas classification, and U.S. Coast Guard regulatory requirements. These design objectives are driven by Coast Guard mission requirements and client requirements. They are also drawn from the 47 motor lifeboat and the 52-foot special purpose craft heavy weather boat that the Coast Guard has used in the past and currently uses. Additionally, we took into account increased awareness of fossil fuel emissions and environmental impact and enhanced endurance requirements compared to the vessels currently in service. Dual control stations ensure redundancy. The BV classification was specified by the client, and the U.S. Coast Guard requirements are not only the flag state requirements, but also the organizational requirements. Next, we'll briefly go over the rules and regulations consulted. In general, we followed Bureau Veritas regulations for classification. Stability-specific rules also included IMO Intact Stability Code. And life-saving appliances and firefighting fell under Title 46 of the U.S. Code of Federal Regulations. Major vessel items and systems include hull and structure, mission systems, accommodations and outfitting, life-saving appliances, and the propulsion plant, electric plant, command and navigation systems, auxiliary systems, armament, and firefighting equipment. The table shown above has our principal characteristics. These were derived from a parametric analysis that was conducted in the second week of the design process. This parametric analysis looked at motor lifeboats used by life-saving services across the world, with special emphasis placed on the Coast Guard's 47-foot motor lifeboat and 52-foot special purpose heavy weather craft. I'd like to also note that the RNLI, Royal National Lifeboat Institution of the United Kingdom, was also looked at closely. The values from our parametric analysis were adjusted to meet mission and client requirements. During this, we found that space was an important factor. Next, we will discuss our mission systems. Our vessel has 3 means of recovery. First is the recovery of persons in the water, which is accomplished by the deck recesses at the side and a Stokes litter on board that can be used with the davits mounted on both the port and starboard sides. Next is dewatering. For this, our vessel is equipped with 2 P6 pumps that can be handed off to other vessels in distress. And lastly, there are towing capabilities. Additionally, our vessel has 360-degree visibility from both the open and enclosed bridges to locate vessels in distress. Additionally, searchlights, floodlights, and communications equipment will assist with finding vessels in distress during nighttime operations. I will now pass it over to Caleb Brockett to discuss the general arrangement.
Thank you, Andre. We will now discuss the general arrangement. The general arrangement was a process that we undertook early on, and from that general arrangement, we further refined our design. As he stated, our design was largely based off of the 47 motor lifeboat, which has been in service for almost 30 years and has a proven track record. We designed it around that specifically so that there was a level of crew familiarity if the design is ever implemented. Moreover, specific considerations included human factors, such as the operation, maintenance, and inspection of spaces. Now, there was a unique challenge for this vessel. We were very space constrained as we had to stick to a similar size as the 47 and 52, but we had more components and mission systems to consider. First, we'll take a look at the profile view. You will see spaces separated by watertight bulkheads with the spacing set by Bureau Veritas. Frame spacing was set at 750 millimeters as per the client. There is a forepeak used for storage and also has the collision bulkhead. A survivor compartment with survivor seating and crew berthing. A mid compartment with a damage control and life-saving appliances locker, workbench and first aid station, head, and small galley. Above, there is an enclosed bridge with controls and communications. Further aft is the open cockpit with controls and communications. Below is the emergency services compartment with access to spaces. Finally, you will see the machinery space and lazarette. Next, we will consider the open bridge deck. You will see searchlights, shock mitigating crew seats and controls specifically to reduce back injuries, and the towing line spool. Next, we will consider the enclosed bridge and the main deck. There are fore and aft gun mounts, aft-facing windows in the enclosed cabin to better view rescue and davit operations, specifically in the side recesses that also have drop-down deck grating for the access on the weather deck. You'll see a Stokes litter for victims, two 2,200 Newton davits to assist in lifting victims and equipment from the water. You'll see a deck-mounted power capstan and two P6 pumps to assist in dewatering. Lastly, we will consider the machinery space and interior deck. There is mass survivor seating, 4 crew racks, a small galley, a workbench and first aid station, a battery bank, the head, the damage control and life-saving appliances locker, and a series of tanks, including the black and gray water tank, potable freshwater tank, fuel tank, and oily waste tank, specifically located here to reduce trim issues. Next, you'll see the twin V drives, which is critical because we were space constrained and we had to fit engines and shafts. The power plants, which were twin Cummins QSM-11 engines, and our hydraulic steering gear. I will now pass the presentation to Mr. Aidan Cavanaugh to discuss lines and structure.
Thank you, Caleb. After developing the general arrangement for our vessel, these characteristics, as well as the general characteristics of the 47 MLB parent vessel, were used to produce a preliminary hull form and lines plan. This lines plan was developed, well, first a 3D model was developed in Rhinoceros 7 using the Orca 3D Hull Assistant tool and the parent hull as mentioned. The vessel is set to be operating in the semi-planing region at design service speed and likely to be planing at maximum speed. So most of the features of the hull form take this heavily into consideration. Some particular features include a V-shaped hull, which helps to mitigate shock from wave slamming, a transom stern, which again helps with better performance in the planing region, and a hard chine, which helps to develop lift, divert spray, and increase the useful deck area on the interior deck. Next, a preliminary GHS analysis was also performed. This was used to get some preliminary hydrostatic information and verify that the hull was likely to meet the requirements of the vessel. Coefficients of form were also derived from this. After producing the hull form and running preliminary hydrostatic analysis, a lines plan was then produced. On the body plan, you can see some important features of the vessel, such as the hard chine and the dead rise, which gradually drops moving aft. This is one of the most important distinctions from the parent vessel, which is a lower dead rise in the aft space of the boat And this was done to, again, increase the useful deck area in the aft section to allow for more machinery. Next, on the shear plan, you can see the stern pattern and the entrance angle at the bow. And the half breadth plan can help give an idea of the waterplane area at different drafts. After this, a 3D rendering was also produced to help with better visualization of the vessel. Next, a structural arrangement was also produced, particularly a midship section. The vessel will be made out of 5083 H116 aluminum alloy. This was selected because of a good combination of strength and weldability while preserving a relatively low cost for aluminum. The vessel will be longitudinally framed, which helps to withstand shock loads from rough seas. The vessel has 750 millimeter frame spacing, as previously mentioned, and plate thicknesses ranging from 8 to 12 millimeters, with the deck plate and side shell at 8 millimeters and reinforced bottom shell and chine platings. The stiffeners are made of 80 millimeter by 8 millimeter flat bar across the vessel. This helps to reduce the complexity and therefore cost of production. There's also a 625 by 12 millimeter central girder. The structural arrangement has a particularly robust design, and this was done intentionally due to concerns for a longer service life. Bureau Veritas NR600 was used to develop the structural arrangement of the vessel. Initially, the client requirements was NR467, but NR600 was used due to the size constraints of the vessel for ships under 65 meters. Additionally, NR561 hull and aluminum alloys was consulted due to the construction of the vessel. A structural analysis was performed by comparing the hull girder bending and shear stresses to maximum allowable values. This accounts for various anticipated loads, such as static loads, such as still water and outfitting, dynamic loads like wave slamming and vibrations from machinery, and various quasi-static loads. Due to the robust construction of the vessel, only global hull girder loads were required to be analyzed due to Rule NR600, Chapter 1, Section 3, 3.1.2, which allows you to ignore local bending stresses on the hull girder if the maximum shear stress is less than 0.35 times the maximum allowable stress. And now I will pass the presentation on to Harrison to talk about weights and centers.
Thank you, Aiden. So for the first step of our weights and centers calculations, we had to divide all of the ship's components up into the ship work breakdown structure groups seen above here. These groups were then applied to a moments and weighted average approach, where each individual component within the group had its weight and location marked, and then we totaled them for the group total. From there, an acquisition margin was placed that can be seen here, and each group received the various acquisition margins. These acquisition margins were determined from a Navy standard for small boats that ensures the vessels are delivered on time and underweight. Each group was totaled to create a lightship condition, which received the service margin. And that service margin was then applied to the total lightship condition, which we can see here. The lightship condition was analyzed for its hydrostatic properties to better understand the vessel in this condition and as a baseline for future loading conditions. The first loading condition we will analyze is a full load departure condition. The full load departure condition was the dead weight added to the lightship weight that was previously discussed. The dead weight is comprised of consumables at a maximum and the waste tanks at a minimum. The maximum and minimum percentages were determined based on customer requirements and previous standards. The full crew and munitions are loaded for a mission. However, there are no survivors because the vessel is departing port and has not completed the mission. Hydrostatic values were assessed for this condition. We received an operating draft of 0.73 meters. This condition was going to be our baseline. And then the next condition our customer asked us to assess that we'll use in the stability calculations is the arrival condition. The arrival condition, similarly to the full load departure condition, had the dead weight added to the lightship. But this time, the dead weight had consumables at a minimum and the waste tanks at a maximum as per the same standards discussed before. You can notice here the full crew is still there. However, there are no survivors. That was because the customer didn't require an arrival condition with survivors. The hydrostatic values were assessed for how the vessel will return back home. And an important note is that the vessel has several other load conditions due to its various mission capabilities. So a future design should look at the various survivor rates as intermediate loads and also various tank percentages in order to determine different ranges the vessel can achieve. These load conditions were then applied to an intact stability test. The intact stability criteria was from IMO, specifically intact stability, Part A, Chapter 2, Section 2.1, where the general stability standards are laid out. These standards were then included in the GHS analysis in order to determine whether they passed or failed. They were input as limits. First, we will look at the riding arm curve for the lightship condition to understand the baseline of this vessel. As you can notice here, the angles of heel go all the way to 180 degrees, and this was important for our future discussion on the self-righting capability of this vessel. A positive riding arm can be noted up until about 75 degrees. The full load departure riding arm curve displayed a similar condition where its positive riding arm was about 75 degrees. The arrival condition stayed within the range with a slightly higher heel angle of 80 degrees. And these three curves display to us that the self-righting capability of the vessel did fail for this pass of the design spiral. The vessel will capsize between 75 and 80 degrees of heel. However, we have suggestions on how we can improve this for the future designs. The structure of the vessel has a lot of buoyant lockers and housing up high that should be accounted for, and this will shift the center of buoyancy from the hull to the superstructure, which will help right the vessel in the capsized condition. The V.C.G of the vessel also needs to be reduced, and this can be done by accounting for the SPC weight that will severely bring down the V.C.G, as well as tank loads and heavy machinery should all be checked to verify they are as low as they can be. A safety feature is that in the capsized condition, the engines will shut off and then automatically restart when righted. This is important in ensuring that we don't damage any of the equipment, or if personnel are in the water, there will be no injuries there. Now we'll move on to the damage stability of the vessel. The damage stability criteria came from two sources. First, we looked at Bureau Veritas NR566, and we found that they had a calculated damage stability approach. However, this did not fall in line with customer requirements, which required a floodable length curve. So in order to apply our floodable length curves, we used CFR, which had a one compartment standard of flooding minimum that can be applied to our floodable length curves. The floodable length curve was taken at full load departure, and as you can see here, the floodable length curves pass. These curves were taken for a two compartment flooding condition. Therefore, we passed the one compartment flooding and survived the damage stability criteria. Now Ali will discuss our auxiliary ship systems as well as machinery.
Thank you, Harrison. So we'll begin with our propulsion system. Our propulsion system uses two Cummins engines, which meets our power requirements of about 500 kilowatts for the two engines combined, as Caleb mentioned earlier. We will be using hydrotreated vegetable oil as our fuel source, as it is derived from vegetable oil and animal fats, so the vessel is compliant with the zero fossil fuel emissions mode. We will be using twin V-drive transmissions, a hydraulic steering gear in the lazarette for maneuvering capabilities, and two Michigan wheel pitch propellers. For our electrical system, we will be using 4 marine cranking amp batteries that are charged by engine mounted alternators. This will be a floating 12-volt DC system, and it will have two conditions, our operating condition as well as an emergency condition. This is shown in our electric plant load analysis, which also includes 6 load categories as well as a 10% service margin on the total. In the next slide, we will be discussing our one-line diagram, which includes a combination of circuit breakers, fuses, and switchboards. So here is our one-line diagram. We will start with the energy sources at the top, followed by all of our different switchboards. The first box is a ship service distribution switchboard, followed by 3 additional switchboards, our propulsion, bilge and emergency, and communication and navigation switchboards. The last box is our auxiliary and deck switchboard and our lighting switchboard. This is followed by all of our loads. Next, we have a battery charger. This is an automatic bus transfer that switches batteries from a power supply and starting mode into a charging mode, and vice versa if the vessel were to capsize and then right again. This is an example of a ground fault detector, which is located on each switchboard. And lastly, we have our circuit breakers and fuses going to each load and switchboard. Lastly, I will be discussing the auxiliary systems. First, we have our HVAC, which is a self-contained marine AC unit. We have our water system, which consists of an oily water tank, a black and gray water tank, and a freshwater tank. Our oily and black and gray water tanks are intended to be on board for the duration of our missions and then discharged at a pumping station. Next, we have our fuel system, which is illustrated in the schematic shown. We have our fuel tank, which is 2,000 liters. We have our filter, which is a raker, duplex combined fuel filter and water separator. We have 2 fuel pumps. These are Viscomat DC gear pumps. We have our crossover for redundancy if anything was to go offline. Again, our 2 Cummins DC engine or 2 Cummins engines, and our fuel return from the engines back into the fuel tank. Thank you so much for attending our presentation. We will now be accepting any questions.
Thank you very much for that interesting presentation. I have a little bit of question regarding the towing. I noticed you mentioned a bit up high. I was curious, the requirement in there for the bollard pull, if it did any calculations on if your engines could achieve the bollard pull. And then also, if you looked at the stability of the vessel due to tow line self-tripping, if the vessel were towing using that bollard pull, that would create any stability implications. Thank you.
So the question was whether bollard pull calculation was performed and if the consideration of towing circumstances were considered when we were doing stability. The answer to that is a bollard pull calculation was done, and we did meet the requirement with excess with our twin diesel engines. However, we would not have accomplished it with only 1 engine running. So the assumption was that we would only meet the bollard pull requirement in a fully operating condition, not a damaged condition or emergency condition. In terms of the stability considerations, we did not yet consider towing in coordination with stability. That was probably something we would consider during the next trip around the design flight.
Thank you.
Yes.
I'm just curious about the exhaust and supply air to the engines. How does that work? How does it secure during a capsule?
Question was, how are the exhaust intakes secured during a capsize event? That was not something we have specifically decided and determined in detail to this date. However, we did do a ship visit to a 47 MLB out east, and we did learn about their use of various cross-through systems, so that if they did self-right, there would be some water that does enter the machinery space, but the bulk of it would pass through. Their intake for their air is actually, I don't know, laser pointer, but if you see the base of the deck house on the aft deck, they actually had a massive intake there. And the idea is when it rolls over, that part would remain just barely out of the water, so that there wouldn't be ingress. Yes.
I wanted to ask about the zero fossil fuels mode. So in your presentation, you mentioned that you would use hydro-treated vegetable oil. Is your solution to always run on that, or is there a plan to have 2 different tanks with 2 different oils? And then I also saw the battery bank for the auxiliary, so that was also a neat solution. Thank you.
Yeah. So the question was if for our zero fossil fuels requirement, we are going to stick with just 1 fuel, or if there is an alternative fuel we're going to use at the same time, and about the battery bank. So we selected HBO, hydro-treated vegetable oil, so that we can basically one-to-one replace diesel, and we were able to select engines from that. And due to our space constraints, we've decided that only one fuel source should be used. So we can run fully off of HVO, and that's all we plan to use. And as for the batteries, we have alternators to charge them underway, but they're going to function more or less as batteries do on vessels now, where we're going to charge them up, deplete them, and use them. But they're just a storage source. We're not really going to be running solely off of electricity ever. They just supply our electrical system. Yeah.
Just a follow-up to that, will you be able to get that preferred fuel at the ports that the vessels kind of use? The same available?
Yes, I can answer that. So the question was how available HVO is and if we can get it at the ports the vessel will be servicing. So I did a study on it when we first were thinking about it. We all looked at different fuels, and we found that HVO was the most producible in the US, and we ended up going with that out of all the other alternatives we were looking at, because we don't have the capability to freeze anything or use any of the cryogenic fuels. So we stuck with HVO, and we found that it is distributable in the US. And the other thing is this vessel is going to be operating at Coast Guard stations. So the Coast Guard can get the HVO and send it to the stations where these surf boats are. There are not many surf boat locations. So the fuel source is available in the States, and the Coast Guard can divvy it up because it's not going to be in high demand among the rest of the fleet.
Thank you.
Wanted to ask what you came off or key improvements in capability or design for 47 foot.
So the question was, what were some of the key improvements over the current 47 MLB for this vessel? The primary requirement that we are meeting as an improvement as for the client is the increased survivor capacity at a maximum of 30 survivors. In addition to this, because of the larger engine space and consequently the larger available engines, the vessel will also likely be able to meet a higher maximum speed.
Additionally, the 47 MLBs currently do not have any overnight accommodations for their crew, whereas our vessel has overnight accommodations, including galley and head, as well as berthings for, which is not something that the 47 has.
And to add actually one thing, when we were visiting the 47 motor lifeboat ourselves, one of the comments was that crew fatigue is a serious concern, and especially the constant slamming that these men and women serving experience when they're underway for significant periods of time can cause significant back issues down the road. So consideration were given to things such as shock mitigating seats to reduce fatigue and injury.
The questions that have come from online. Is there a suitable location in the deck house to place a survivor on the deck in the stove slip?
The question was, is there a suitable location on the deck house to place a survivor in the Stokes litter? We have a larger length than the 47, and visiting the 47, we actually discussed their operations with operators aboard the 47 MLB team. The Stokes litter on the aft deck can be placed, so if you had helicopter operations, they can drop it down there. And then the purpose of having the aft deck being the place where the Stokes litter gets placed for victim retrieval or operation is that from there you can place them into our survivors compartment and give them care inside should the conditions be too dangerous outside for the crew to assist them with.
Okay, next question. The two bridges appear to hinder the visibility of farmland. Seeing forward from the open bridge to the bow is obstructed by the enclosed bridge, and the open bridge blocks visibility aft from the enclosed bridge. Have you considered methods to mitigate these interferences?
So the question was, what are we doing to consider the impact that the open and closed bridge have on each other's visibility? In terms of the open bridge or the closed bridge, there wasn't all too much we could do about that one, just because we wanted to fit two full decks on top of each other. With the current, with the 47 MLB, the interior deck is very short because it's not meant to house people for a long time. But due to our longer service life, we wanted to have a little bit more space on the interior. We did have a conversation with our mentors about potentially raising up the open deck so that there was more visibility on the forward end.
And that's definitely something we want to consider in the next run of the design spiral. The only problem we have to be very careful of with that is that would even further reduce our GMs and make it even less likely for us to be self-writing, which, as we discussed, is already kind of a problem.
Okay, next one. Please explain the LCG appears to be about 33% of the length overall, which is very far out. And determined by the bow seems to be contrary from the LCG condition. Were the lines adjusted for such an LCG?
Yes, sir. So as we talked about, one of the design considerations that we made very early on in the vessel, which in hindsight we maybe shouldn't have done, is that the vessel has a very low dead rise in the aft. And the unfortunate consequence of that is that it increases the submerged volume, particularly in the aft end, which of course forces the LCB equally farther aft. So although the LCG is very far aft on the vessel, the LCB is even farther, which does cause the vessel to be trimmed by the bow. So a potential solution to that would be sort of just progressing back to what previous vessels have done and increasing dead rise in the aft section of the vessel.
Two more here, so let's see if we can get through them in the next couple of minutes. Talking about your self-writing capability. That the question says, I haven't seen the math, but if you properly accounted for the buoyancy of the deck house, I suspect you really do have a self-writing vessel. Deck house buoyancy is critical, and the challenge is about making the deck house watertight and strong enough for the rollover event. Keeping systems functional and preventing free flooding through ventilation is a big battle. So that was more of a comment. Yeah, the next one is a little bit more of a comment. I'll just go over air intake and exhausts about rollover that was addressed. With a full load of survivors, what is the estimated effect on the stability? Is stability still positive, and by how much?
I can take that one. So the question was, with a full load of survivors, what is the effect on the stability, and is the riding arm still positive? So to answer that question, that falls under the intermediate loads that we are not required by the customer to analyze. However, going past concept design to preliminary stages, it is the most pressing intermediate load because our full load departure condition is not traditional to other vessels where you have a commercial tanker, you might be leaving with everything and then coming back with less. This vessel is going to see its highest weight, as directed by the question, when it recovers these survivors. So I would suggest that should be the first step of our next stability analysis when we assess the vessel.
It is worth adding there that when we have a full load of survivors, the vast majority of them would be in the forward survivor compartment, which is the lowest compartment in the vessel, tied to the machinery space. So although we haven't done a direct analysis on it, we do have a pretty good excess of stability in the upright condition at the moment. So I wouldn't suspect that adding a lot of weight down low in the vessel would be too much of an issue for stability.
Thank you very much.